Okay, so in this video, what I'm going to do is basically give an introduction to sigma notation and how it works. So here we go. What sigma notation is it's a big Greek capital letter sigma that stands for summation. And it has a start value and a stop value, which is typically denoted n when it's not specified. So an example of how this would be used is, let's say you wanted to add up the numbers 1 through 6. You would write 1 plus 2 plus 3 plus 4 plus 5 plus 6, and then you could sum them all up like that. But what if you wanted to add up all the numbers from 1 to 100? Well, you'd be here all day doing 1 plus 2 plus 3 plus 4 plus 5 plus 6, dot dot dot, 96, 97, 98, 99, 100. So they invented the shorthand, which would be sigma notation. And the way this works would be, instead of writing that, I'd say the sum of k is equal to 1 to 100. And what this does is it iterates through. First it plugs in 1 for all the values of k, so it goes 1, and then k iterates to 2. So it plugs in 2 for all the values of k, plus 2. And it sums whatever this is, so plugs in 3, plus 3, and then it goes all the way out, 99, plus 100. So it goes on like that. And this becomes important in calculus with calculating Riemann sums. And before we get into that, though, there's 3 important sums that you need to know. And that is the sum of the first in numbers, which would be this. This is something that comes up a lot in calculating Riemann sums. From k equals 1 to n of k, the first n squares, k equals 1 to n k squared, and the sum of k equals 1 to n of k cubed. So what this would do is adds up the first n numbers. So it goes 1 plus 2 plus 3 plus 4 plus 5 dot 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 n minus 1 plus n, like that. Now, there's got to be a formula for this, otherwise it would be very tedious to have to write all this out. And actually there is. These are called triangle numbers, and there is a formula for triangle numbers, and I'll show you one easy proof of it. If I write this whole sequence in reverse, n plus n minus 1, well, here, I'll make sure it's symmetrical. Hang on. Okay, so 1 plus 2 plus 3 dot 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 n minus 2 plus n minus 1 plus n. We all agree that this is the sum of the first n numbers. Then I write this in reverse underneath, n minus 1, n minus 2, dot dot dot, 3 plus 2 plus 1. If we added all these together, right, like so, this, we begin to notice a pattern here. That really, these two are just, this is n plus 1, this is n plus 1, and we do that how many times? Well, we do it n times. So the total sum of these two rows is n times n plus 1. Now, we've summed up each row twice, basically, because we have two rows and we found the sum of both of them. So we divide by 2, and this is the sum of the first n integers. So the sum k equals 1 to n of k is equal to n times n plus 1 over 2. And this is something you probably should memorize for computing Riemann sums. It really comes in handy. And the rest of these I won't prove because they're a bit more difficult to prove. So I'll just give the answer. K equals 1 to n of k squared. So this would be the first n squares. So 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to n squared. This is equal to n times n plus 1 times 2n plus 1 all over 6. And again, this is just something you need to memorize for computing Riemann sums. The first n cubes, and you'll start to notice a little pattern here of what this looks like. This is going to be 1 cubed plus 2 cubed plus 3 cubed, dot, 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 to n cubed. Well, this is equal to, actually, the square of this sum. So that's what that's equal to. So these are three sums that you probably should know for computing computing limits of Riemann sums. And yeah. So I'll work some problems on finding the limits of Riemann sums in the next video.